So in part A, you've been asked to, using a tangent line approximation at t equals 5, estimate what the radius of the balloon is at 5.4 seconds. And so you can think about 30 feet as the radius at t equals 5. So it's going to be more than that, because at 5 seconds, the rate of its increase in feet per minute is 2. So then we're going to add on to that 30, 2 feet per minute. Well, we're looking for units of feet. So the only way to get rid of this minutes here is to multiply by the 0.4 minutes that happens between t equals 5 and t equals 5.4 that we're looking for. And that answer is 30.8, just like it shows here in the key. So if you got 30.8, that's going to be worth 1 point. Now as we think about answering the second part of part A, we had this tangent line approximation that had a y-intercept of 30 and was increasing at this slope of 2. But they also tell us that the graph of r, the radius, is concave down. So if we were to sketch something that's concave down, it would be looking like the blue. Concave up, of course, would look like the black. That's not what we want. So we can see that our approximation over here at 5.4, assuming this is 5, is going to be considerably higher than the actual answer. This is our actual. This is our estimate. And so that's why we would say that the estimate is greater than the actual radius at 5.4, but we would need to use this information that r is concave down to get full credit. So for part B, you're asked for the rate of change of the volume of the balloon with respect to time. So that means we are going to take the derivative of this entire equation with respect to time. On the left, we'll get dv dt, and on the right, we will get 4/3 pi r squared. This 3 will come down and cancel out with the 3 in the denominator. But because we're differentiating with respect to t, we're going to get a times dr dt, which is the rate of change of time. Since they gave us the time they wanted, 5, then we know that the radius at 5 was 30 from part A, but we also know the rate of change of the radius with time was 2. We used that in part A too. It came right from our table. So when you do all of this math, you get 7,200 pi feet cubed per minute. Why is it feet cubed per minute? Because feet cubed is a volume unit and minute is our time, all coming from dv dt. Now, how should you score yourself? If you took the derivative with respect to t, that would be 2 points. Probably what the AP board scored this is if you got this first part that I'm boxing out in blue, that would probably be worth 1 point. And remembering the derivative with respect to t, dr dt, that was probably worth 1 point. And then your answer here, including the units, was worth 1 point for your total of 3. So in part C, they've told you to use a right Riemann sum of 5 subintervals. So that means we're looking at this being the left and this being the right for the first rectangle. And then this being the left and the right for the second, left and right for the third, left and right for the fourth, left and right for the fifth. So we'll end up using this height, this height, this height, this height, and this height. And that's what shows up in the work here. Your answer should have been 19.3 feet, and you'll get 1 point for that. And then you were asked, using correct units, explain the meaning in terms of the radius. So if we are summing up feet per minute times minutes, of course the minutes will cancel out and we'll just be left with feet. So that's going to be the change in the radius from 0 to 12 minutes. Or you could say over 12 minutes, the radius increased in length by 19.3 feet. 1 point for something like what you see in blue, or what they said in their key. So for part D, you're asked if your approximation in part C is greater or less than this integral. And as we look at a sketch that I've drawn, we can see that there's all of this leftover area until we get to the very bottom, where there seems to be a little extra area between 11 and 12. And so it appears as though we should answer that this is an underestimate, or, as they say in the key, 9.3 is less than the actual integral. But we need to give a reason to get the 1 point that's available here. And it comes from the fact that the graph of R is concave down. So R is my radius. If we were to graph some kind of radius function, we started at 30, and we know that we're going up because we've increased by 19.3 feet in radius, but they tell us R is concave down. So as we think about this, our slope is increasing at a decreasing rate. So all of these numbers are positive, but they're getting less and less and less, which shows in our table. These are all positive, but they're getting less and less and less until we get to here. This appears to be a little bit of a problem with their problem, actually. And so because R is concave down, then we can say R prime is decreasing. And that's how we would finally get our last point, an underestimate because R prime is decreasing. And then I made an error as I explained parts B and C. You did not have to give the units in parts B and C to get full credit. You could have just had the answers, the numbers, for parts B and C, but now to get this last point on the rubric, when you look at parts B and C, you'd need to have feet cubed per minute to get this last point on the rubric. This entire problem was worth 9.